velocity potential also, right? So from previous one, we have proved that your stream function satisfies your continuity, and velocity potential satisfies your what? Irrotational flow conditions. Correct or not?
Yes,
So yeah, this is what. So I just want you to write a small definition for FlowNet because I explained it, but still I thought that if you can write it, these are some important point of that which you have in the slide. But apart from that, you just write few lines for that. So you can note down the heading FlowNets. So it is an orthogonal network. It is an orthogonal network in bracket grid bracket closed, obtained by drawing a series of streamlines and equipotential lines equipotential lines is called a flow net. Full stop. It is customary. It is customary to keep the chains in their values same between adjacent equipotential lines equipotential lines and adjacent streamlines full stop. The streamlines are drawn by dividing the space between the boundaries into a few equal number of flow channels equal number of flow channels full stop. Then the equipotential lines then the equipotential lines are drawn orthogonal to streamlines intersecting the boundaries taking the care that the flow fields are
Sir, your voice is not clear. Sir, your voice is breaking.
No, sir, it is
is
okay.
clear actually. You just keep quiet. Intersecting the boundaries, taking the care that the flow fields are roughly squares in the region of uniform flow, full stop, as the velocities at various points as the velocities at various points in the flow are inversely proportional to the spacing between the streamlines and equipotential lines between the streamlines and equipotential lines, full stop. The network is useful to estimate the velocities at different points in the flow field to estimate the velocities at different points in the flow field when it is not convenient to use analytical method. So this is what we explained in the last class also. I explained all these terms also, but still I thought that let's write something for that. Most of the parts are there in the slides. So we were talking about the flow fields. So here we wrote just now that velocities at various points are inversely proportional to the spacing between the streamlines. Means if you see this slide here, so if you have the stream function here, so here you have psi equal to 120, and then the another one psi equal to 90, then 60, then 30. So can anyone tell that what is happening between psi 120 to 130? Where are we moving about actually? Can anyone think? Then based on this streamlined flow pattern, can anyone think that what is happening, what type of flow is it actually? Or where is the surface and which direction we are moving? Anything from your side? Any answer? No answer from anyone? Any guess? Palvi or Ishwar Mittal or Arun Pandey? Some of the name I remember. Harpreet also and Gurneet. Anyone can answer something? No one wants to say anything.
Sir, actually, I lost most of the thing which you dictated today.
Today I
That
have
is why I
not
am unable
dictated
to understand
anything.
properly.
Today I have not dictated anything for your kind information. I have just repeated what we have covered in the last class. I have not
Still,
taught
sir, your
anything new.
voice is fluctuating for me, sir. I am unable to understand.
Okay. What about others? Okay, you are not able to understand. What these other people? Or they don't know anything also. That is also one thing. So everything has gone on top of head and people has not understood anything after conducting I don't know how many classes. We are just talking these kinematics from last, I hope from 1 month maybe. Anyway, good output. So here, what you have here, where the stream function is actually value is high, it means that particular streamline is moving faster. So it is somewhere actually there your velocity need to be very high actually. So very high velocity mostly are being found where you don't have any obstructions or you means practically free from surface or maybe that surface might be moving with that velocity. Means that surface cannot be stationary, so that's the end of that particular part or either free or maybe moving with some velocity. So that is point here psi equal to 120. Now here psi equal to 130 means you are moving close to a particular surface where uh, either you are moving to close by or if it is the end of the flow actually, so it means that surface is also moving with this particular velocity actually, because from this side that velocity can be calculated. Now, what happens in between of this? Here you see that the streamline, the gap has been increased sufficiently high here. So these are the zones where your velocity magnitude has been decreased between the two means streamlines due to change of directions. So for that to cover up your flow rate, because flow rate going between two the streamline need to be conserved. So therefore, you are covering a more area so that more fluid can be taken out with that because that is the continuity part here. So they need to satisfy your continuity. So therefore, the streamlines here is far away here. Now you see the first one here. There are not much change here. You have nearly same here. So gap between these. So wherever the streamlines are getting apart, it means those are the zones of low velocity zones. So to cover up the things, the streamlines goes far apart actually. Now, as you see this flow net, so if you see this, if you will see this one, this looks a perfectly square type of thing. So in the drawing with these flow nets, you just draw the means the square thing. So in that way, it is easy to calculate because you are just moving a same distance to x and y directions. So in that case, you can calculate easily your velocity at these different points. So that is the usefulness usefulness of the flow net. So your purpose is your means one of the means assignment to all of you is that you have to find a problem which use the flow net to calculate the velocity. That is the assignment to you. How to find, where to find, it is up to you. So that need to be submitted by next Tuesday. You have to find at least one problem on that way. Now I can tell here from this is equipotential lines, which is phi value, means the value of the potential function is minus 60 along this entire line. So once you know that, you can calculate velocity easily at all these particular dot points. And based on that also, because you can calculate what is the value of the stream function also, because these are means intersecting each other at the 90 degrees. So you can calculate your value of the stream function also. And finally, you will calculate your velocity here. So these, once you will solve a problem, you will come to know how to use it actually. Next part here, you can say that rectilinear flow here. So let's say basic flow pattern. What could be the basic flow patterns of the flowing fluid? One could be, let's say, completely in the straight line. So either it may go to in direction X or maybe your direction Y, maybe your direction Z. So I just wrote for one here. So this is rectilinear flow, practically in X direction. So here you wrote V vector is V I cap only. And based on that, you can write your psi. So psi, expression of psi would be what? Your u is given what? Velocity u in terms of psi? Del
minus
psi upon
d del
no,
psi over del.
del psi upon del y, right? So it's not minus there.
Yes, sir.
Okay, so you will get psi function there. So you will get that, and velocity potential is always perpendicular to that. So you have just put v with in x direction or means of only. So if you have psi here, you have just here you got the velocity potential in that way. Another flow pattern could be a completely vertical. So you have kept a j cap there, and then you calculate psi and phi. These are means some ideal type of flow pattern, either completely in x direction or bidirectional. Practically, it doesn't happen actually because you always have some sort of fluctuations. So you always have some x and y components. So that's the means the another flow pattern that you may have some angle of inclination actually there. So you have x velocity component can be calculated from v. If v this side, you have the alpha there. With the horizontal, you can calculate u is v cos alpha and v is v sin alpha actually. So you can calculate again your psi and phi. Now the another part, one is called a source, one is called a sink. So source is the place from where your fluid is coming out. So that's the source. Okay. So just like in case of a pipeline, so you are pumping the fluid from one of the ends. So that end from where the fluid is coming is called a source. The other ends where the fluid is going out, that's called a sink because something is coming in. So sink is something is coming in, source is something is coming out from there only. So this is a, you can say, a source here. So from here the fluid is coming out and is getting spreaded actually. So this is what you have here, just like a pipe. So you have a pipe, pump the fluid. After that, you don't have a connection. So fluid is leaving out in a circular path from here, because it may, sometimes it may go up for a particular side. So that's one thing. So let's say sometime you are spreading the fluid in a horizontal plane. So that's called a circular source only. So what you have here, that as you will move away from the center, your velocity will keep on decreasing. So your velocity would be a function of r. So as you will move far away from the center, your velocity will continuously keep on the decreasing. That's what you have here. The ur is q upon 2 pi r. What is q? Q is total flow rate, and 2 pi is entire the theta actually, because total flow rate is getting distributed equally in entire circumference. So that is 2 pi. So that q upon 2 pi is called the strength of your source. Okay. So the actually the strength of the source is nothing but the flow rate per unit width per unit time. So that's called q upon 2 pi in case of the circular case, or a point center source actually. As you will move away from the center, your velocity will keep on means keep on decreasing. So velocity is actually inversely proportional to r actually. So if you want to calculate velocity at a particular r, you are calculating q upon 2 pi r. Now, as you have moved to a particular r, you can move in a particular circle, full circle there. Your velocity is not getting changed, only its direction is getting changed, the orientation only. So at a particular r, you can draw a equipotential line. So that's what here, each circle is a equipotential line. So from there, your potential function is just will have some value there. Some value is your value of the velocity. Now, only thing here is direction is getting changed. Magnitude is same. Okay, sometimes it would be this side, then this side, then this, because your theta is getting changed. So your value is same. Only sign is getting changed. Therefore, though each ring is called equipotential line, it's phi actually, which is a purely a function of r only. And whatever is coming out from center is your psi. That's your the streamlines. So streamlines are going in a outside from the center only. Okay. So this is for source case. Same thing can also be possible for a sink, because the sometimes from all the sides when we have let's say we are pouring the water, or best way that the sink of your kitchen. You fill up the water, and from all sides of your means the entire tub, you have a fine hole in the center. All water is going downside, so everything is coming in. So that if you will invert the direction of this flow, then it will become the sink actually. So this is the sink. So in case of sink, the flow is coming completely inside, and only thing your direction of velocity now getting the reverse only. So as with the minus sign only, and that means the strength is again same, the q by 2 pi. So this is the two simple example of source and sink. Another examples, I think, is it visible, or shall I zoom it?
Zoom it.
Okay. So what to do? So this is actually, this part we already talked about that. So we talked, this is actually your, in case of source part, fluid is leaving outside of that. This is the sink part, we already talked about that. Then this is the another part here, that you have here the rotational flow. So rotational flow you have in this, you are moving a flow in a circular path here. So here, no velocity component in direction r, so you don't have a r component. But you have a component in theta sides, velocity in theta side actually here. Can you tell how would you calculate the velocity in theta side? Anyone can calculate the velocity in a circular path? Array, have you heard the term V equal to R omega or not?
Yes, sir.
So what is why are you taking that much time? You know that if you have a circular motion, you know the angular velocity. You can calculate the linear velocity V equal to R omega. So that is your theta component. For that also you can calculate the equipotential lines. So what will happen to equipotential lines? So your each circle would be the equipotential line, because at a particular R your velocity is not getting changed only. Okay. So the another type of thing here, can you see what is this here? It have both. It have both the things. It have a circular component also. You see the direction also. It is moving on the circular side. It has another component also that you see here. The something is also going outward also. How can it be possible?
Sir, in a fountain.
Fountain, you are putting it outside, so things go. One component goes to vertically up, and does it move? I don't hope.
Sir,
Move to nahi karta? Yeah, in a fountain with a rotating disc, that's possible.
Yes.
Okay, so that's called a doublet actually. You have two things. Something is coming out, at the same time you are also rotating it also. Okay. So these are some actually cases where so we were here actually. So these were the some cases for that. So you can have the many more. So simple definition of source and sink. Source, something is coming out. Sink, something is going on. Flow patterns, you can identify where the velocity in magnitude is getting changed. Now you draw the point where velocity is not getting changed. That's called your equipotential lines or equipotential lines or curves, whatever you say for that. Fine. So let's see. This is the one of the problem actually. We want to practice what we have covered in previous two classes actually. So this is what a velocity potential is given to you. That phi is given to you in terms of this. Now you have to verify it first whether it is incompressible flow or not. First you have to verify this, and after that you have to obtain a corresponding stream function also. What would be the stream function for this particular flow? So can you people do that incompressible flow, what would you check?
Sir, u plus v is equal to 0 proof करना.
What?
Del dot v equals to 0.
No, that is
Sir,
not the
u plus v is equal
flow.
to 0.
U plus b, no, that is इस टाइप का तो कोई रूल ही नहीं है. U plus b equal to 0.
So del u by del x plus del v by del y is equals to 0.
Yes, that is your continuity equation for incompressible flow, right? So del u upon del x plus del v upon del y must be equal to 0 for your incompressible flow, right? That is your continuity for xy plane. So you have phi. So first you have to calculate what is your u, what is your v. So do you know the expression how to calculate u in terms of phi?
Yes, sir.
So what is expression? So u is minus del phi upon del x. and V is minus del phi upon del Y, right?
Yes, sir.
So calculate those first, and then after that, the substitute those actually in your continuity equation. Let's see whether it is satisfy or not. All of you should try and just do it. In meantime, अभी मैं थोड़ा attendance ले लेता हूँ आप लोगों का आज कौन-कौन है at least. Let's see how many people are physically present. Can you note down this 5 so that I can change the slide?
1 minute, sir.
Yeah.
Done, sir.
So yeah. So in meantime, you people should continue. You should find the expression for your U and V, and then you have to satisfy your continuity. Astha,
Yes, sir.
Abhishek,
Yes, sir.
Abhishek Saini,
Present, sir.
Aditya Kumar Mishra,
Present,
Ajay
sir.
Yadav, Ajay Yadav,
Yes, sir.
Amgod Ganesh, Anirudh Pal, Anurag Singh,
Present, sir.
Arshpreet Kaur,
Present, sir.
Arun Pandey,
Present, sir.
Balbinder Kaur,
Yes, sir.
Chandresh Sharma,
Yes, sir.
Chirag,
Yes, sir.
Chirag Sethi,
Yes, sir.
धैर्य,
Yes, sir.
ये नाम ठीक प्रोनाउंस किया है धैर्य धार्य व्हाट योर नेम
Sridharya.
ओके दिनेश कुमार
Yes, sir.
दिनेश कुमार यादव
Yes, sir.
3 पॉइंट है उसमें कौन
ईश्वर मित्तल
Present, sir.
ग्लोरिया
Present, sir.
गुंटू राजू
Present, sir.
हर्षित डोडियार
Yes, sir.
ओके हरसिमरन कौर
Present, sir.
हिना जिंदल
Present,
Yes, sir.
आप हिना जिंदल हो ओके जसनप्रीत सिंह जसमीत सिंह
Yes, sir.
जयेश कुमार
Yes, sir.
कामले प्रजोत राजेंद्र
Yes, sir.
what should I say to you Prajot or what's your name Prajot right
Sir. Yes, sir. My name is Prajot.
yeah rest of your surname something
Yes, sir.
Connect Jaiswal
Yes, sir.
Kari Jaswant
Yes, sir.
Kari or Carry
Curry. It is
okay.
curry, sir.
Kashish Singla,
Yes, sir.
then Kora Hari Krishnan. Krishna Singh,
Present, sir.
Lavisha,
Yes, sir. Present, sir.
Malhar,
Yes, sir.
Manisha,
Yes, sir.
Manoj Kumar,
Yes, sir.
Manu Sharma.
Present, sir.
वो हो गया क्वेश्चन, बीच बीच में बता देना कि देन वी विल कंटिन्यू फ्रॉम देयर.
Yes, sir.
Then Monu Prajapati,
Yes, sir.
Midushi Sharma,
Present, sir.
Mohit Kumar,
Present, sir.
Mokshit Khanna,
Yes, sir.
Nancy Burma, Nidhi,
Present, sir.
Nikhil Kumar,
Present, sir.
Nishant,
Present, sir.
Nishjit Singh,
Present, sir.
Omandeep Singh,
Present, sir. It's Sumandeep.
okay, sorry, Omandeep, okay, Palvi,
Present, sir.
Pankaj Kumar, Pashubala Rasmi, so Rasmi I can say,
Present, sir.
okay, Pranab Gera,
Present, sir.
Keval Pratap Singh,
Present, sir.
Radhe Krishna,
Present, sir.
Raghav Sood,
Present, sir.
Roshan Kumar,
Yes, sir. Yes, sir.
Ravi Meena, Rishabh Goyal,
Yes, sir.
Ritika Agarwal,
Present, sir.
Sahil Malhotra, Malhotra actually, Sahil, Sakshi, no, Saksham Sikri,
Present, sir. Present, sir.
okay, Sandeep Kumar,
Yes, sir.
Saujanya Verma,
Present, sir.
Soumya,
Present, sir.
Shivam Kumar Mishra,
Yes, sir.
Shubham Chaudhary, Simran, Srishti Basist,
Present, sir.
Steffi.
Present, sir.
How is your handwriting? Because one of the the Steffi I taught in Thapar, her handwriting was very, very just like a doctor's actually. How is yours?
So you can check my assignments.
Okay, I need to check them also. क्विज भी चेक करके आपका मार्क्स भी देना है ना मुझे. और you know the marks, I think the some of the quiz you may got the marks जो ऑनलाइन लिया था.
No, sir.
No, sir.
Okay, I
No,
will
sir.
check this weekend I will finish all the part. Suresh,
Yes, sir.
Takdeer Singh,
Yes, sir.
who is this? Subham Chaudhary, mic is not working fine. Tanishta Gupta,
Present, sir.
Tiratpal Singh,
Present, sir. It's Tripat.
how to pronounce?
Tripat.
Tripat, okay. Ujjwal Deep Pandey,
Present, sir.
Utkarsh,
Present, sir.
Vaibhav Kumar Jain,
Yes, sir.
Ben No, Ashok Kumar would be better.
Present,
Ashok
sir.
Kumar,
Yes, sir.
yeah, okay. Varun Kapoor,
Yes, sir.
Bikramjeet,
Present, sir.
Vineet Kumar,
Yes, sir.
Binita Ratan,
Present, sir.
Bipin Singh,
Yes, sir.
Yatharth,
Present, sir.
क्या बात है, ब्रेकफास्ट नहीं किया? बड़ी धीमे से आवाज आई आपकी। खाते पीते रहिए, okay? So, we were here. I hope some of you might have solved it. So, for incompressible flow, you have to check your continuity. So, continuity for 2D flow in xy plane is del u upon del x plus del v upon del y for incompressible flow, okay, equal to 0. So, for that you need u. So, u in terms of phi is minus del phi upon del x, and v is minus del phi upon del y. Later on, if you want to write for the stream function, so in terms of that, your u is given del psi upon del y, and v is given minus del psi upon del x. So first part, I calculated your u by the derivative of phi with respect to x with minus sign. So I got this actually. I hope you might have also got the same thing.
Yes, sir.
Yeah, I guess
Yes, sir.
सभी का u. Okay.
Yes.
Yes, sir.
So same way you might have calculated your v also. So once you have u and v, so then you are further differentiating them, because you have to find del u upon del x further. So you will differentiate them with respect to x again. So with respect to x again, you will get your del u upon del x would be this term here. You got this? Del u upon del x?
Yes, sir.
Then you are calculating again your del v upon del y. So that's coming this much.
Yes, sir.
After that, you use your continuity of the left hand side part. So del u upon del x plus del v upon del y. Add these two terms, and finally I am getting is equal to 0. It means it is 2D incompressible flow in xy plane. Okay?
Yes, sir.
Yes, sir.
So next part of that is to find the means the stream function. So stream function के लिए you already know that u is del psi upon del y. You already know expression of u. Integrate that. So your psi is given by that way. So one of the part of psi would be u dy, because you have u is del psi upon del y. So integrated with respect to y, you will get a function of x. So this is the one of the expression of psi. Another expression of psi would be from a v component of velocity. So that's it from here minus because v is minus del psi upon del x also. So the integrate that with respect to x and put a function of y. So you will get two functions of psi, and finally you should club them together, and let's see what is coming. So anyone has calculated this first from based on u actually? Anyone has tried this? You have u is minus
Yes.
u is del psi upon del y. So integrate that with respect to y. So if you integrate that, you are getting this minus 6x5y plus 20x cube y cube minus 6x by 5 plus a function of fx, which we don't know actually. Okay?
Yes, sir.
Yes, sir.
Now do the same thing with V actually. So V is minus del psi upon del x. So do that part also. So based on V component, your psi is minus V del x into dx, integrate that, and plus a function of y actually. So if you will do that, integrate this particular part here, you are getting minus 6x5 x to the power 5 y plus 20x cube y cube minus 6x by 5 plus a function of gy. Okay.
Yes, sir.
So can you compare previous expression or this one? Previous was this one. Are those same or different?
Same,
This
sir.
is
Only the
one.
last added term is different.
Last term, which term?
Sir, that gy and
It's
gx
same.
term is different.
Oh, that's okay. So now we are coming to that. So this psi is already have x and y, right? Yes or no?
Yes, sir.
So obviously, so they didn't have any exclusive function of purely y and not any exclusive function of purely x. So they have a mixed function. So mixed function is common to them. So finally, you have taken a common component, and exclusive component of y and x is not there. So you have just actually have put equal to 0. Okay.
Okay, sir.
So that way you have found your distinct function based on your velocity potential. Now the next component of your once so far we did so almost everything about this kinematics, that motion, velocity, circulation, type of deformation of the fluid, acceleration, velocity field, everything we did in that category. Now the one of the major part of that, once we are making a flow, we want to measure it actually. So we want to measure it. Previously we did everything in terms of analytical part there. So analytical velocity expression, acceleration part there, force also there, drag force, velocity. So every part we did analytical expression part there. Now we want to do the how do we do the measurement there. So in case of flow, first part is there, flow meter. We are interested that how much flow is just flowing. So first thing we want to find in terms of, let's say, volume also, or maybe in terms of mass. So flow meters are two category. One is a mass flow meter, which directly give you the how much quantity is flowing. And one was just a volumetric flow rate. So let's say in case of petrol, you are talking about in terms of volume. In case of oil, you are considering in terms of kg or volume.
So volume.
Yeah, so all the liquids most of the time are being measured in terms of volume actually, because density you can say that most of the time is flexible because based on your temperature conditions also in there. So sometimes depending on the place from where to where you are moving it. So based on that you are actually but if a volume quantity you have fixed, you can calculate density at that particular temperature, you can calculate its mass actually. So most of the time is volume quantity is being the measured in case of the liquids actually, which is easy to measure actually. You need not to do any other operation, just collect in a container. You can already mark them in terms of volume or in terms of height. That's easy actually conversion. That's actually you can say primary measurement. If you want to convert it in terms of mass flow meters, you have to have an online meter just to have a density. Multiply with that, you can calculate your mass also. So to have a mass flow rate, you have to put some additional measurement in that particular part. So first category of flow meters, one is the flow meters which will directly give you your volumetric flow rate. Other one is just once we also need to calculate the velocity also, because previous one everything is being calculated from the velocity, your point velocity, your flow rate, your is the stream functions. There you are calculating the velocities. So we should have some meters just to calculate velocity. So in case of velocity, you have this one is this here insertion meter. So this is actually just a pitot tube actually. So this will calculate the velocity in a fluid at any point. Just dip it at that particular place, you will calculate the velocity. How does it work? I will show you actually. So one is called full bore meter, means that's, let's say I can show you. So full bore meter category, you have these actually two things, venturi meters and the orifice meter. One is called the nozzles. So nozzles is just a contractions there. So from there you can just calculate the flow also. That's just like a binotch and let's say orifice also, small hole. So we will just come to know that particular part also. Then you have the area meters. So area meter case, your area of flow meters is also getting changed. So in that category, you have the rotameters. Also, I will show you one or two and then we will end just here only. So this is, I will end here only. So what we have a full bore meter, this is a flow meter. So it's known as venturi meter. These are two ends. One is here, one is this particular part. So if you see the diameter at both the ends are same, it means it has the diameter same of the diameter of the pipe at both the ends. What is happening in between, that's for timing, you just leave it. So these are called full bore meters. Okay, these are fitted in the pipeline at a given particular place where you want to measure the flow rate. And diameters are same. They are the diameter of meter and diameter of pipe are same. Therefore, these are treated names as full bore meters. Okay. So it's working and how to do the calculation of that, we will do in the next class for that. Anything you want to ask?